Okay. Yes, since this is the extensive air shower session, probably everybody of you knows CORSIKA and has used it for hit at least a couple of times. CORSIKA was originally developed for the Cascade experiment in the 1980s and has been at the core of the simulation chain for many air shower experiments over the last decades, and has received dedicated maintenance from the people at Karlsruhe. And as you can see by the number of citations that the CORSIKA report receives every year, it has become a kind of common reference frame for the community. But CORSIKA has its limitations. It is a hand-optimized code, which means it is really fast, but it is not. It is not always really flexible. It is a monolithic Fortran code with several dialects mixed. The program options are heavily intertwined in the source code, and maintaining incredibly large monolithic Fortran source code is becoming increasingly difficult. And also the parallelization possibilities of the Fortran versions of CORSIKA are limited. There is MPI parallelization, but there is no multi-threading, no GPU parallelization. And for this reason, since a few years now, we have started to rewrite CORSIKA in modern C++, and focus on writing it modular and flexible, and taking into account the needs and the possibilities of modern supercomputing, in particular the parallelization. And this effort is coordinated from KIT, but there is a strong community integration. And this diagram sketches the overall structure of this new framework, and all these modules are designed so that you can exchange one of the modules for another of the same kind of module. Now CORSIKA 8 has both hadronic and electromagnetic cascades available. We are doing extensive validation by comparing to CORSIKA 8 and also to other codes like ZHS or Connex. Actually, this way, a few bugs in CORSIKA 7 have been found and fixed. And some of the possibilities that we have with CORSIKA 8 now already go beyond what was possible with CORSIKA 7. For hadronic cascades, we have the usual suspects of the high energy hadronic interaction models available. At the moment, we have only URQMD as a low energy hadronic interaction models, and Sybil 2 3D and Pythia 8 for the decay. And the new possibilities we have in this regard are a complete genealogy of particles, stuff that goes beyond only knowing the mother and grandmother particle that you have in CORSIKA 7. The atmosphere can be much more flexible than the several layers of exponential atmospheres. And we can also simulate showers in different media, and I will showcase this now with a few plots. Here you see a comparison of the particle spectra for a 10 to the 18 electron volt vertical proton shower, comparing CORSIKA 8 to MCEQ and CORSIKA 7, and the overall agreement looks rather good. And here you see an example of the genealogy of muons. And we can see here which ancestor particles contribute to the muons that we observe on ground, and also how they are distributed over the energy, and also by the shading which are contribute to the particle skin and which to the antiparticles. Once for the whole shower, and once for the muons more far away. And this is an example for an air shower transitioning from air to water, something that also was not possible with CORSIKA 8, with CORSIKA 7 so far. In CORSIKA 7, the electromagnetic cascades had been treated by a modified version of EGS4, which was heavily integrated into the source code, and which was modified by adding several important processes like muon pair production, photoelectronic interactions, and optionally the Landau-Pomeranchuk-Migdal effect. And in CORSIKA 8, we are now using the lepton propagator proposal, which originally comes from the underground experiments and originally focused on muons and leptons, and which now does the propagation of electrons, positrons, muons, and photons in CORSIKA 8. We do not yet have all the possibilities of CORSIKA 7 available. We can do the Landau-Pomeranchuk-Migdal effect at the moment only in media with homogeneous density. For inhomogeneous media like the atmosphere, that's a work in progress. Here you see the comparison of the longitudinal profile of 1 TeV electromagnetic showers between C7, C8, IRIS, and ZHS. And here we see the charge excess, which is of particular importance for radio. And with regard to the radio calculation in CORSIKA 7, CORSIKA 8 aims to overcome several of the limitations that we currently have in CORSIKA, and which also Washington just mentioned, the things like the Higg radio signals being reflected or from upward going showers. The curvature of the curved propagation of the radio signal, or showers crossing from the air to dense media like ice or water. And in CORSIKA 8, the radio calculation is a process like the others, and it is also implemented very flexible. We have two algorithms: the Correa's algorithm as in CORSIKA 7, and the ZHS algorithm as in ZH-IRIS, and both formalisms are in good agreement. And in principle, every part of these can be exchanged for user written routines, if that is makes sense for the application at hand. Like for example, the track filter might usually selects only the electrons and positrons, but if you have some application where you want to do some additional filtering on that, that is in principle possible. Here you see the comparison of radio pulses between ZH-IRIS, CORSIKA 7 with Correa's, and CORSIKA 8 with the two formalisms from the workshop we had 2 weeks ago. And here also the frequency spectra. And the agreement is not perfect, but it is reasonable, I think. And we also have 2 implementations of Cherenkov emission available. They are in good agreement with each other and also with CORSIKA 7. And one of these modules is parallelized using vectorization, and the other is parallelized using GPU parallelization. And the development of CORSIKA 8 happens as an open source project. So everybody can download the source code and work on it himself from the GitLab server. We meet bi-weekly via Zoom to discuss new developments or validation, and we communicate via a mailing list and a Slack channel. And if you want to take part in this, just reach out to the steering committee. I'm one of the members of that. That was the status part of of this presentation and the prospects of what we are planning to do in the future are performance optimization. Of course, CORSIKA 8 is not yet as performant as CORSIKA 7, which has been optimized for decades. We want to improve the treatment of multiple scattering. We want to implement the Landau-Pomeranchuk-Migdal effect also for inhomogeneous media, and we are working on interfaces to several low-energy hadronic models. Pythia 8 is already well underway, and Fluka and Sophia are planned for the near future. And for photohadronic interactions, currently we are limited to calculating only the secondary particles at high energies, but when we add Sophia, that will change. And in conclusion, I'd say that for developers now is a really great time to join the effort of writing CORSIKA 8. End users should probably have a little more patience before they start using it. CORSIKA 8 is capable of simulating complete showers, and already some of the capabilities go beyond what is possible with CORSIKA 7. Thank you.